Hi everyone, and welcome to this episode of Keipert Labs. In today's video, we're going to be discussing the concepts around nuclear power. That is, generating electricity using nuclear energy in the form of uranium. Okay, so let's recap some of the ideas that we've introduced so far. Okay, so introducing the idea that some elements are radioactive. The nuclei of their atoms are naturally unstable, and in order to become more stable, they give off radiation. And that radiation can be in the form of alpha, beta, or gamma radiation. Okay, we've looked at the idea that we have uranium in particular is an element of interest. And so uranium is our heaviest naturally occurring element. It is also naturally radioactive in all of its isotopes. But the one that concerns us the most, or the one that we're most interested in terms of this effect, is called uranium-235. And the reason that we're interested in it is because of the concept of nuclear fission. Okay, so where we're talking about the idea of splitting the nucleus, and thinking about the amount of energy that gives off, okay? And relating back to Einstein's most famous equation of E equals mc squared, which helps us to explain where the energy comes from. Okay, so we're going to look at it in terms of, right, well, how do these concepts lead us to a way to generate electricity? Okay, and so we're going to just quickly focus on that concept of nuclear fission as a way of thinking. Okay, well, it comes down to an energy source at the start. Okay, so nuclear fission. Okay, so that idea of splitting the nucleus. Okay, so we've got a nucleus of uranium-235. Okay, this is its nucleus. And then what comes along and happens is that, let's say, this is total to scale, just be mindful of that. Let's say that this represents a neutron. What happens to the nucleus of uranium-235 is if a neutron comes along and impacts this nucleus, which is already naturally very unstable, what it does is it causes it to split into two smaller nuclei. Okay, so depending on exactly how that comes about, they may be, there's a range of different elements that could end up being. Okay, in order for this to happen. So splitting into these sorts of ones. And what they also give off is it gives off more neutrons that also happen. So I don't have 3 blue buttons, but you can imagine. Okay. In this process, we're making splitting off 3 neutrons during this process. And then also what we're doing is we're giving off an intense amount of energy. I realize that's not actually very visible for you. Sorry about that. Okay, so what happens? The reason that we give off energy is that a small amount of mass inside this nucleus during this process gets converted to energy. Okay, what Einstein was able to show with his equation is that mass and energy are actually a lot more closely related than we thought, and that when we look at E equals mc squared, which is energy is equal to the mass times the square of the speed of light, which is a very, very large number, that then a tiny fraction of mass can produce an intense amount of energy if it's converted this way. And so what that does is that then this energy has to be given off in some form. Okay, so that can be given off in the form of gamma rays. Okay, but also it gets given off in the form of heat or thermal energy and light. And so what happens is that we, particularly if we're looking at this idea of heat, that we can harness this splitting of uranium as a source of heat or thermal energy. Okay, so the way that works, or the way that we take advantage of that, is that we have inside a big kind of container, okay, we have these, so we have this water kind of filled tank. these are what's called our, so we put the uranium into this rod kind of shaped form. Now we call these uranium fuel rods. Okay, so they're immersed in this kind of this water solution, this water that's kind of surrounds them. All right, and so the idea is that this uranium is naturally very reactive. Now, so when we looked at this idea that our uranium can split into two smaller nuclei, and then we give off our few neutrons, the danger of nuclear, this process, comes from these neutrons going on to interact with three others. But what then happens is that, so that's where we get a chain reaction that occurs. But if we could take two of these neutrons away from this process, and then this interacts with the uranium that then can split into smaller ones, it gives off three neutrons, and we take two of them away, so that this then goes to another one, and so on and so on. What we get is that we get a continuous reaction. Continuous reaction. Okay, so that we get a series of controlled splittings, okay, so that controlled fission. And what happens then that this heats up the water. We use this energy, this thermal energy, to heat up water, which then forms steam, which then turns a turbine, okay, which generates electricity. Okay, so when we generate electricity from burning things like coal, we burn coal to heat up water to form steam, which turns a turbine, which generates electricity. Yeah, so when we're using burning things like coal, we're using this same sort of process. So a different form of energy that's used to heat up water and do this process as well. So all we're doing here is that we're using this natural breaking down process of uranium and using it to help generate electricity. Now, the main thing that's really an issue with this is that making sure that this stays controlled. Okay, so we've seen in the past that when it's uncontrolled, we get a nuclear, the intense release of energy that's involved in a nuclear weapon. So we need to be able to have a way to carefully control this process so that that cannot occur. And so what we do is that we have what we call control rods. Control rods. Okay, so the idea is that these absorb the extra neutrons. That we position them around and in between the fuel rods so that these extra neutrons that are given off by the breakdown of the uranium are soaked up so that they can't go on to then, in an uncontrolled manner, cause other things to break down. Okay, so these can be raised or lowered. So that depending on, in a way to kind of control the reaction. And if the reaction needs to speed up a little bit, we can remove them a little bit to try and encourage it along. If it's getting out of control, we bring them back down so that then we can absorb more of those neutrons and slow it down. It's all about helping to maintain a water temperature so that then this reaction can happen. Now, the other reason that this water is here, because the idea is that as the water gets heated up, then there's this, then we can form steam kind of elsewhere. But this water is mainly here to help for cooling. So this is as a coolant. So by having this water that surrounds it, that some of that thermal energy gets absorbed by the water, and so that then by continually pumping fresh, cool water around, and causing the water to be always cold, that then it can absorb a lot of that thermal energy before it has a chance to become dangerous or out of control. And so, yeah, by continually kind of cooling it down, that's another control mechanism that we can use. And what we've seen in the past where different accidents have happened with nuclear power, it's where the cooling mechanism has failed. Okay, and so that then the temperature in this situation gets out of control, and so then that causes the fuel rods to melt down because of the intense heat, and then basically the reaction gets out of control and an explosion can happen. Okay, such as in Chernobyl in 1986, and then there's been some other accidents in the past where that sort of thing has happened as well. Okay, but so basically the essence is that we're using fission in a very controlled way by controlling the number of neutrons that are around in order to, as a source of energy to heat up water that forms steam, turns a turbine and generates electricity. All right, thanks very much for watching. Bye for now.